You have been told that space would freeze you in an instant. It is one of those facts everyone simply knows, and it is wrong. Out past the last planet, farther than anything we have ever built, a spacecraft called Voyager 1 has been sitting in that so-called killing cold for almost 49 years, and it has not frozen. It is still warm inside, it is still working, it is still whispering back to us across 16 billion miles of nothing. The truth about why is stranger than the myth, because the emptiness out there cannot steal a machine's warmth the way you imagine, and so Voyager's life and its death are being decided entirely from the inside by a small fire that no one can ever refill. So here is the question for tonight. If the cold out there cannot kill it, then what is quietly, and certainly, running it down? Get comfortable and settle in. If you have not subscribed yet, subscribe and stick around. Because to understand why this one small machine is still warm, we have to overturn almost everything you thought you knew about cold and fire and how long a made thing can possibly last. Let's begin. Part 1. A Voice. From the Edge. Right now, as you settle in to listen, a machine older than most of the people watching this is whispering to us from a place so far away that its voice takes almost a full day to arrive. It is called Voyager 1, and it left Earth on the 5th of September 1977, back when the fastest way to share a song was to hand someone a cassette tape. It was built to last 5 years. It has now been running for close to 49 of them, and tonight, as you lie there, it is still going, still moving, still sending home the faintest thread of a signal across an emptiness that has no real end. Nothing we have ever made has travelled farther. Nothing we have ever made has held on longer. And the strangest part of the whole story is not how far it has gone. It is that, out there, in the coldest and emptiest place we have ever reached, the little machine is somehow still warm. Let me tell you where it actually is, because the number is difficult to feel until you slow it down. Voyager 1 is now more than 25 billion kilometres from the Sun, which is a little over 16 billion miles. To put that in something you can almost hold in your mind, it is more than 4 times farther out than Pluto ever travels, so far that the Sun, from where the spacecraft sits, is no longer a warm and blazing thing at all. From Voyager, the Sun is just one more bright point of light among thousands, giving no more heat to the spacecraft than any other star in the sky. There is no daylight out there. There is no warmth arriving from anywhere. And yet the machine keeps its own small warmth, hour after hour, year after year, the way a coal keeps its glow long after the fire around it has gone dark. The distance is so enormous that the mission is no longer really measured in kilometres. It is measured in patience. When engineers on Earth want to tell Voyager to do something, they send a radio command travelling at the speed of light, the fastest thing there is, and that command still takes around 23 hours to reach the spacecraft. Then the answer has to come all the way back, at the same speed, taking another 23 hours. So a single question, and its reply, a simple, "Are you there?" and a simple yes, now cost the better part of 2 full days. Later this year, in November of 2026, Voyager 1 will cross a line that no object built by human hands has ever crossed before. It will be 1 full light day away from us. The distance light itself travels in 24 hours, which means a message will take a complete day to arrive. Think about that. We're about to have a conversation partner so far away that the words take a day to land, and still it answers. That is the thing I keep coming back to, and the thing this whole video is about. This is not a dead relic tumbling silently through the dark. It is awake. It is listening. Every so often it gathers up a little strength and sends a whisper of data back toward the small blue world it left behind almost half a century ago, and enormous dish antennas here on Earth, the only ears sensitive enough to hear it, catch that whisper out of the noise and read it. The message it sends is, in effect, always the same underneath all the numbers. It says, "I am still here. I want you to hold on to that phrase because we are going to come back to it. Still here." It is the quietest kind of miracle, and it is running on borrowed time. Let me put the sheer improbability of that into words, because it is easy to let it slide by. This spacecraft was designed, by engineers working in the 1970s, to survive for about 5 years and to visit 2 planets. 5 years. That was the promise, the whole intended life of the machine. It has now outlived that promise nearly 10 times over. Think of everything that has happened on Earth in those 49 years. Every person born and grown old, every song written and forgotten, every device you own invented and then made obsolete, and through all of it, without a single pause, this one small machine has kept flying and kept talking. The computer that runs it is so old that the phone sitting next to you right now is millions of times more powerful. The entire memory it thinks with is smaller than a single photograph you would casually take today. And yet that ancient, tiny, hopelessly outdated machine is doing something no newer, faster, smarter machine has ever done. It is calling home from the space between the stars. Nothing else we have ever built has even come close. And here is what makes the warmth so remarkable, once you set it beside the age. For all those 49 years, the small fire inside the spacecraft has never once been relit, because it was never lit in the first place, not in the way we light a fire. It has simply glowed, continuously, since before the launch, never flickering, never going out, never asking for a single thing from anyone. While the world turned over back on Earth, while whole generations came and went, that quiet warmth just kept pouring out of the machine's core, holding the cold at bay, hour after hour, year after year, decade after decade, with a patience that has no human equal. So when you hear that Voyager is still warm, understand what that does and does not mean. It is not a machine being recharged, or refueled, or tended like a campfire that someone keeps feeding. It is a single fire lit once by physics rather than by any hand, that has burned without interruption for longer than most marriages last, in the coldest place we have ever reached. Understanding how that is even possible is the whole of what we're here to do tonight. So close your eyes for a moment, if you are somewhere you can, and let me take you out there, to where it is. Imagine you are floating in the space between the stars, far past the last planet, far past the edge of everything the sun holds on to. There is no wind here, because there is no air. There is no sound, because there is nothing to carry it. The sun is behind you somewhere, a bright star no wider than a pinprick, and it warms you not at all. The nearest other star is so distant that even moving faster than any human machine has ever moved, it would take you tens of thousands of years to reach it. Nothing has touched this place in a very long time. Nothing moves here that we did not send. And then you see it. A small shape drifting in the dark about the size of a compact car, with a wide white dish held out in front of it, like an ear turned patiently back toward home. Its edges are worn by decades of tiny impacts too small to see. It is old. It is alone. And when you drift close enough, you notice something that does not belong in a place this cold. Far inside its body there is a faint, steady warmth, a low red glow of heat that has never once gone out. In a universe that offers this spacecraft nothing, no fuel, no sunlight, no help of any kind, it has carried its own small fire the entire way, and that fire is still burning quietly right now as you listen. It has kept this machine alive through a cold with no edges, and it asks for nothing from the darkness around it. It simply holds on. That warmth is the reason Voyager is still speaking to us. It is also, as we are about to see, the reason it is dying. Those two facts are not separate. They are the same fact, wearing two faces, and untangling how something can be kept alive and killed by the very same thing is going to take us into some of the most beautiful and unsettling physics there is. But before we get to why the machine is still warm, we have to talk about how many times, just in the last 2 years, it has very nearly gone silent for good, and about the small group of people on Earth who refuse to let that happen. Because Voyager 1 has not simply drifted along, untouched and trouble-free for half a century. Lately it has been failing. Lately it has been coming right up to the edge of death, again and again, and every single time something has pulled it back. And the story of how it keeps returning from the brink is where we have to begin. Part 2. The Machine That Keeps Refusing to Die. In November of 2023, Voyager 1 stopped making sense. For weeks it had been sending home its usual stream of data, a steady packet of numbers describing its own health and the strange environment around it, and then, one day, the numbers turned to nonsense. The signal was still there. The spacecraft was still pointed at Earth, still transmitting, still alive in every way that mattered. But instead of readable information, it was sending back the same meaningless pattern over and over, a flat repeating loop with nothing inside it, like a person who is clearly awake and clearly trying to speak, but can only produce a single syllable again and again. The machine had not gone quiet. It had, in a sense, forgotten how to talk. Imagine being one of the engineers who saw that first garbled transmission come in. You cannot walk over and look at the patient. You cannot open it up, run a diagnostic, or swap a part. Your patient is 16 billion miles away, and every question you ask, it takes the better part of a day to arrive and another day to answer. If you try something, and it works, you will not know for 2 days. If you try something, and it makes things worse, you will not know that for 2 days either. This is medicine practiced across an ocean of time, and the body on the table is a computer built in the early 1970s, running on a design older than almost everyone still trying to save it. For months, the team worked the problem blind. They knew the trouble lived in one of the spacecraft's 3 onboard computers, the one responsible for gathering up all the data and packaging it neatly for the trip home. But they could not see inside it. So in early March of 2024, they tried something clever. They sent up a command that engineers described in plain language as a poke. It was a gentle nudge that told the computer to run through its programming in a slightly different way and send back a complete readout of its own memory, raw and unpackaged, whatever state it happened to be in. It was a long shot, and when the reply finally crawled back to Earth a day and a half later, they decoded it, and they found the culprit. About 3% of that computer's memory had gone bad. Somewhere in the physical hardware, a single tiny piece had failed, one stuck bit, one sliver of a memory chip that would no longer hold the value it was supposed to hold. It may have simply worn out after 47 years of faithful service. It may have been struck by a cosmic ray, one of those high-energy particles that race through the space between the stars and occasionally punch through delicate electronics. Nobody can say for certain. But that one damaged spot happened to store a piece of code the computer needed in order to do its job, and with that code corrupted, the machine could no longer assemble a coherent sentence. A single failed fleck of memory, smaller than a grain of rice, had silenced the most distant object in human history. It is worth pausing on how strange the situation was for the people trying to fix it. When your laptop starts behaving badly, you can restart it, run a diagnostic, look up the error, or in the worst case carry it to someone who can open it up. None of that exists here. There is no restart button you can simply press and watch reboot, because pressing it means sending a command that will not even arrive for the better part of a day, and whose result you will not see for another day after that. There is no opening it up. There is no one to carry it to. Every move in this repair was a message dropped into a well so bottomless that you had to wait a day and a half just to hear the splash. The engineers had to imagine, in complete detail, the inner state of a computer they could not see, reason out what must be wrong from a trickle of clues, design a fix, send it into the silence, and then wait, knowing that if they had guessed wrong, they might not only fail to help the spacecraft but actively push it further toward the edge. It is problem-solving of a kind almost no one else on Earth will ever practice, carried out with the patience of people who have made peace with the fact that every conversation takes days. And the fix itself, when you understand what they did, is quietly astonishing. They did not have a spare chip, and they could not install one if they had. What they had was the rest of the computer's memory, most of it still working, with small gaps of unused space scattered here and there. So they took the piece of software that had been living in the broken region, the piece the machine needed in order to speak, and they carefully cut it apart into sections small enough to fit into those scattered gaps, and they placed each section wherever there was room. And then they rewrote the machine's own instructions so it would know to gather the pieces from their new hiding places and run them in the right order. They rebuilt a working mind out of the broken one, not by replacing anything, but by rearranging what was left around the wound. And they did it across a gap of 16 billion miles, working in a computer language older than most of them, and it worked. Now here is the problem, and it is the kind of problem that has no good answer. You cannot replace the chip. There is no repair crew. There is no way to reach out across 16 billion miles and solder in a new part. The damaged memory is damaged forever. So the engineers did the only thing they could do, and it is genuinely one of the most remarkable feats of improvisation I have ever come across. They took the piece of code that had been living in the broken section of the memory, and they carefully broke it up into smaller pieces, and they tucked those pieces into other corners of the computer's memory that still worked, scattered across whatever empty space they could find. Then they rewrote the connections so the computer would know where to look for each piece, stitching a working mind back together around the dead spot in the middle of it. They were in effect performing surgery on a brain from a day and a half away, moving thoughts out of a damaged region and into healthy tissue, and hoping the patient would wake up able to speak. On the 20th of April 2024, after sending up their fix and waiting out the long silence of the round trip, they got their answer. Voyager 1 began speaking clearly again, for the first time in 5 months. The nonsense was gone, the numbers made sense. The most distant machine we have ever built had been brought back from the edge of a permanent, meaningless silence, not by force, not by luck, but by a group of people who understood a 50-year-old computer so intimately that they could rearrange its memory in the dark. And barely a year later, it happened again, in a completely different way. This time the trouble was not the mind, but the muscles. Voyager steers itself using small jets called thrusters, tiny puffs of gas that let it turn its body and keep its big dish antenna pointed precisely back at Earth. Without them, it drifts, and a drifting spacecraft eventually points its ear away from home and is lost. The thrusters it had been relying on were slowly clogging up, choked by a fine residue that builds up after decades of firing, like a faucet slowly closing with mineral deposits. They were running out of push, and the obvious backup, a second set of thrusters meant for exactly this situation, had been declared dead more than 20 years earlier, back in 2004, after a small heater that kept them working had failed. Those thrusters had sat cold and unused since then, written off, considered gone. In the spring of 2025, running low on options, the engineers decided to gamble on the dead. They reasoned that if they could gently warm those long-abandoned thrusters back up, coax some heat back into them, they might just fire again. It had never been tried. There was a real chance the attempt would fail, or make things worse, and there was a hard deadline pressing down on them, because the single giant antenna on Earth powerful enough to command Voyager, a 70-metre dish in the southern hemisphere, was about to be shut down for a year of upgrades. If they did not attempt the fix before that antenna went offline, they might lose the chance entirely, and the spacecraft along with it. So they sent the commands, and they waited out the day-long delay, and then they watched. And the thrusters that had been considered dead since 2004, cold and silent for over 20 years, warmed up and fired. The team described it, without much exaggeration, as a save with almost no margin left, a rescue that came together in the last possible window before the door closed. I want to slow down here, because it would be easy to hear all of this as a story about clever machines and heroic engineering, and to miss the quieter thing underneath it. This is really a story about people. There is a small team of men and women who have spent, in some cases, their entire working lives on this one spacecraft. They keep a 49-year-old machine alive by sending instructions into a silence that takes a full day to answer, and then waiting, and then finding out whether their patient survived. Many of the people who designed Voyager, who knew its every quirk because they had built it with their own hands, have long since retired, and some of them have died. The people who tend it now are often reading manuals written in the 1970s, in the language and shorthand of engineers who are no longer here to explain what they meant. They are keeping faith with a machine that is older than they are, carrying forward a promise made before many of them were born. There is a particular kind of devotion in that, and I think it deserves to be named. Out there, farther than anything else we have ever touched, a small warm thing is slowly running down, and here, on Earth, a handful of people refuse to let it go dark alone. They cannot see it. They cannot reach it. They can only listen for its voice, send their careful instructions into the dark, and wait most of 2 days to learn whether it heard them. It is one of the longest acts of care in the whole history of exploration, a vigil kept across a gap so wide that saying "wake up and hearing I am awake" takes 2 full days. And they keep it, year after year, for a machine that most of the world has quietly forgotten is even still up there. But here is the question that all of this circles around and never quite answers. The engineers can rewrite its memory, they can revive its thrusters, they can fight for it with everything they have, and yet none of that would matter at all if the machine were not still warm, still powered, still generating that faint, steady glow of heat that keeps its electronics from freezing solid in a place hundreds of degrees below zero. Every rescue depends on the machine having enough warmth and enough power to be rescued. So the real question, the one hiding underneath every dramatic save, is not how they keep fixing it. It is why it is still warm enough to fix it all. Why has the coldest, emptiest place we know not simply frozen this little spacecraft into a lifeless block of metal long ago? That is the question almost nobody thinks to ask, and the answer is stranger than you might expect. Part 3. The question. Nobody asks. Almost everything you have ever heard about Voyager is a story about distance, how far it has gone, how fast it is moving, how many billions of kilometers now separate it from the planet that made it. And those are wonderful facts worth marveling at, because the scale of them really does bend the mind. But I want to point out something curious about them. Distance is the easy question. Distance is the one everyone asks because it is the one that fits neatly onto a graphic, a number that gets bigger every year. The harder question, the one that almost nobody thinks to ask, is not where Voyager is. It is how Voyager is still working at all. Consider what should have happened to it. This is a small machine sitting in the emptiest, coldest environment we have ever sent anything into. The temperature of the space between the stars, the background chill left over from the birth of the universe itself, sits at only about 3 degrees above the coldest temperature that is physically possible. A temperature so low that the very idea of cold almost loses its meaning. Everything we know about cold, from our own lives, tells us what should happen to a warm object left in a place like that. It should freeze, quickly, completely and permanently. Leave a cup of coffee on a table on a winter night, and it goes cold in an hour. Leave a person outside without shelter in a hard freeze, and they are in serious danger within minutes. So a delicate machine, full of fluids and electronics that only work within a narrow range of temperatures, sitting for nearly half a century in a place unimaginably colder than any winter night on Earth, should have become a frozen, lifeless artifact a very long time ago. Let me make that cold real for a moment, because the numbers are hard to feel. Scientists measure the coldest possible temperature, the point where all heat is gone, and they call it absolute zero. Nothing can be colder than that, anywhere, ever. The empty space that Voyager drifts through, the general background of the universe far from any star, sits at only about 3 degrees above that absolute floor, 3 degrees above the coldest anything can be. On the scale we use for weather, that is more than 270 degrees below the freezing point of water, a cold so complete that ordinary matter barely knows how to behave in it. Air itself, if you brought it there, would freeze into a solid. There is no winter on Earth, no polar night, no mountaintop, that comes within 100 degrees of it. This is the environment the spacecraft has been sitting in, unprotected for close to 50 years. By every instinct we carry about cold, it should be a frozen ruin. And notice how confidently we predict that, based on nothing but everyday experience. We know in our bones what cold does to warm things. We have watched soup go cold, and puddles turn to ice, and breath fog, and fingers go numb. We have a lifetime of evidence that cold is fast and greedy, and takes your warmth quickly. So the survival of a warm machine in a place that cold feels like a violation of something obvious, a rule everyone knows. Which is exactly why the answer is so interesting, because the rule everyone knows turns out to be a rule about Earth, not a rule about the universe. Down here, cold really is fast and greedy. Out there, it is neither. And the reason for that difference is the first of the 2 secrets we need, the one that overturns your intuition about what cold even is. Let us start there, with the cold itself, and with why the emptiness of space is nowhere near as good at freezing things as you have always been told. And it hasn't. That is the thing. It hasn't frozen. It is still warm inside, warm enough that its fuel is still liquid, warm enough that its electronics still run, warm enough to gather its thoughts and send them home. Something is keeping it warm out there, in a place that by every intuition we carry should have chilled it to death decades ago. So the question on the thumbnail of this video, the question you may have clicked on almost as a joke, turns out to be one of the most interesting questions in all of space exploration. Why hasn't it frozen? The answer comes in 2 halves, and both of them are going to overturn something you probably believe about how the world works. The first half is about the machine itself, about what it carries inside it, a small and quietly astonishing source of warmth that needs nothing from the universe around it. The second half is about the nature of cold itself, and it is the part that surprises almost everyone, because it turns out that nearly everything we assume about the cold of space is wrong. Space is not a hungry freezer that rips the warmth out of things. It is something much stranger and much more patient than that. And once you understand both halves, you arrive at the truth hiding inside the title of this video, the genuinely unsettling thing that gives the story its weight. Because the answer to why has it not frozen and the answer to why is it dying turn out to be the exact same answer. The thing that keeps Voyager alive is the thing that is killing it. Not two separate forces, one good and one bad, fighting over the fate of the spacecraft. One single process, doing both at once, inseparably, on a schedule that was fixed before the machine ever left the ground. That is the terror at the centre of this, if you want to call it terror, though I think by the end you may find it is something closer to a strange and quiet kind of beauty. It is the recognition that the fire keeping something alive can also be the clock counting down its death, and that sometimes those are not two things but one. To see how that works, we have to start with the cold, because the cold is where the surprise lives. We have to throw out the idea we all carry, the picture of space as a bottomless freezer that turns warm things to ice in moments, and replace it with what is actually true. And what is actually true is that space, for all its menace, is a terrible thief. It is very, very bad at stealing warmth. It does not attack the heat inside a spacecraft and tear it away. It cannot. The rules of physics simply do not let it work that fast. Instead, it does something far more patient, and in its own way far more haunting. It waits. Let me show you what I mean, because once you see how heat really moves, and why the emptiness of space changes everything about it, you will never look at the cold the same way again, and you will finally understand why a warm little machine can hold its warmth for 50 years in a place that should have frozen it in an afternoon. Part 4. The cold that will not take your heat. Here is the first thing you have to unlearn. Cold is not a substance. It is not a thing that flows into objects and fills them up. When you step outside on a freezing night and feel the chill sink into your hands, it feels exactly as though cold is pouring into you, like water into a sponge. But that is not what is happening at all. There is no such thing as cold, not really, not as a thing in its own right. There is only heat and the absence of heat. What you feel on that winter night is not cold arriving. It is your own warmth leaving, being carried away from your skin into the colder world around you. Cold is simply what it feels like when something is stealing your heat, and that changes everything, because it means the real question is never how cold is a place. The real question is always how good is this place at taking my warmth away. So how does warmth actually leave an object? It turns out there are only 3 ways it can happen anywhere in the universe, and their names are worth knowing because the whole survival of Voyager depends on them. The first is conduction. Conduction is heat moving through direct contact, warmth passing from one touching thing to another. When you hold a warm mug, heat conducts from the mug into your hand. When you sit on cold metal, your warmth conducts out of you into the metal. Conduction needs touch. It needs stuff pressed against stuff, so the heat can hop from one particle to the next like a bucket brigade passing warmth hand to hand. The second way is convection. Convection is heat carried away by a moving fluid, by air or water flowing past you and sweeping your warmth off with it. This is why a cold wind feels so much colder than still air at the same temperature. The moving air keeps stripping the warm layer off your skin and replacing it with fresh cold air to be warmed and stripped away again. It is why you blow on hot soup to cool it, and why a fan cools you on a hot day. Convection also needs stuff. It needs a fluid, a sea of air or water, in constant motion, to carry the heat off. And the third way, the last way, is radiation. This one is different from the other two, and the difference is the whole story. Radiation is heat leaving as light. Every warm object, including your own body right now, is constantly glowing. Not with visible light, but with invisible infrared light. A soft outpouring of heat radiating away in every direction as electromagnetic waves. This is what a night vision camera sees when it picks out a warm body in total darkness. You're glowing, faintly, all the time. And here is the crucial thing about radiation, the thing that makes it unlike the other two. Radiation does not need any stuff at all. It does not need something to touch. It does not need air or water to flow. Light can travel through completely empty space, which is exactly why the light and warmth of the sun can cross 93 million miles of nothing to reach us. Radiation is the only one of the 3 that works in a vacuum. Now put those 3 facts together and point them at Voyager, and watch what happens. Voyager sits in the space between the stars, which is very nearly a perfect vacuum, emptier than anything we can create in a laboratory on Earth. There is almost nothing out there. A few stray atoms drift through each small volume of space, but for all practical purposes the spacecraft is surrounded by pure nothing, and in pure nothing, 2 of our 3 ways of losing heat simply stop working. Conduction is gone, because there is nothing touching the spacecraft to conduct heat into. There is no cold ground, no cold air, no cold anything pressed against it to drink its warmth. Convection is gone too, because there is no fluid, no air, no water, nothing to flow past it and carry its heat off. 2 of the 3 thieves of warmth cannot even enter the room. There is a consequence of this that surprises almost everyone, and it flips the usual fear on its head. Spacecraft close to Earth, and even astronauts on spacewalks, often have more trouble getting rid of heat than keeping it. On the sunlit side of a spacecraft, sunlight pours in and warms it, and because there is no air to carry that warmth away, the heat just builds and builds, with nowhere to go except the slow trickle of radiation. The great space stations we have built have to carry enormous radiator panels for exactly this reason. Wide fins whose only job is to glow waste heat away into space, because without them, the stations would slowly cook from the inside, overheated by their own machinery and by the sun, unable to shed the warmth quickly the way anything on Earth can. Read that again and let it sink in, because it is the opposite of what the movies taught you. The problem in space is often not that things freeze too fast. It is that they cannot cool down fast enough. The same emptiness that we imagine as a killing freezer is actually so bad at removing heat that engineers spend a great deal of effort just trying to help their machines get rid of it. Now radiation, the one path that does work, deserves a closer look, because its slowness is the entire reason Voyager has survived. When a warm object radiates its heat away as infrared light, the rate at which it loses that heat depends on how hot it is. A very hot object, glowing red or white, radiates its warmth away quickly, pouring out light. But a cool object, only mildly warm, radiates very slowly, giving up its heat in a lazy, unhurried trickle. Voyager is not hot. Its interior is kept at a gentle, livable warmth, not much different from a cool room, just enough to keep its fluids liquid and its electronics working. And an object at that mild temperature, radiating into the dark, sheds its heat with extraordinary patience, a little at a time, over long stretches. So the spacecraft is not fighting a losing race against a fast and greedy cold. It is quietly topping up a slow and gentle leak. As long as its small fire produces heat, a touch faster than the spacecraft lazily glows that heat away, the balance holds and the machine stays warm. And for 49 years that is exactly what has happened. A slow leak and a slow fire, held in a quiet balance across half a century of dark. That leaves only radiation. The only way Voyager can lose heat, the single remaining path, is to slowly glow that heat away as infrared light, shedding it into the darkness one soft wave at a time. And radiation, compared to the other 2, is slow. A warm object surrounded by cold air loses its heat quickly, because the air is right there, touching it, flowing past it, hauling the warmth away by conduction and convection. But a warm object surrounded by nothing can only radiate, and radiating is a patient, gradual business. The heat leaks out, but it leaks out slowly, over hours and days, not seconds. You already know a machine that works on exactly this principle, and you probably have one in your kitchen. It is a thermos, a vacuum flask, the kind of bottle that keeps coffee hot for hours or ice water cold all day. Have you ever wondered how it does that? The secret is in the walls. A thermos has a double wall of glass or steel, and between those 2 walls the air has been pumped out to create a vacuum, a thin shell of empty space wrapped all the way around the liquid inside, and that vacuum does exactly what the vacuum of space does. It blocks conduction and convection. The heat of your coffee cannot conduct through a gap that has nothing in it to conduct through, and it cannot be carried away by air that is not there. The only way for the warmth to escape is the slow way, by radiation, and so the coffee stays hot for hours instead of minutes. A thermos keeps things warm by surrounding them with a little bubble of nothing, and that is the astonishing truth about Voyager. The spacecraft is sitting inside the largest thermos imaginable. The empty space around it, the very thing we imagined as a killing freezer, is actually one of the best insulators in existence. That same emptiness that makes space so hostile to life, the absence of air, the absence of everything, is precisely what stops it from ripping the warmth out of the spacecraft. Space cannot conduct Voyager's heat away, because there is nothing to conduct it into. Space cannot convect it away, because there is nothing to flow. All space can do is patiently wait for the spacecraft to radiate its warmth away on its own, slowly, over a very long time. The emptiness that should have been the enemy is, in a strange way, the spacecraft's protection. I want you to feel this, not just understand it, so let me take you back out there for a moment. Imagine you are floating in that same emptiness, drifting beside Voyager, far beyond the planets. You have always been told that space would freeze you in an instant and you brace for it, expecting the cold to hit you like plunging into an icy lake. But it does not come. There is no wind here to bite at you, because there is no air. Nothing is touching you to pull the warmth from your skin. The cold does not rush in because there is no cold to rush, only emptiness that cannot reach you. Your body simply begins very slowly to glow its warmth away into the dark, shedding heat as invisible light, the way a stone gives up the warmth of the day long into the night. It would take long minutes, even hours, for that slow radiating to chill you through, not the instant killing freeze of the movies. The danger here is real, but it is not the danger you were told to fear. And this is the part that unsettles me, and I think it will unsettle you too once you really sit with it. The emptiness of space does not attack you. It does not fight you for your warmth. It is not cruel. It is something worse than cruel. It is indifferent. It will not tear the heat from your body. It will simply, patiently, never give any of it back and wait for you to run down on your own, like a clock winding out. The deadliest cold in the universe kills not by force but by absence, not by taking but by refusing to return. It is a cold with no edges and no hunger, and it does not need either, because it has all the time there is. Everything that survives out there survives on the warmth it brought with it, and only for as long as that warmth lasts. Which brings us right back to Voyager, and to the real question underneath everything. If space cannot easily steal the spacecraft's heat, if the emptiness is actually protecting it, then the whole matter of life and death comes down to one thing, and one thing only. It comes down to the warmth the machine carries inside itself, the small private fire it brought from home. As long as that fire makes heat faster than the spacecraft slowly radiates it away, Voyager stays warm enough to live. So what is that fire? What has been generating heat inside a machine for nearly 50 years, with no sunlight, no fuel deliveries, and no way to refill it? The answer is a substance so strange and so quietly powerful that holding a piece of it in your hand would feel like holding a coal that never goes out, and it is time to look at it directly. Part 5. The fire it carries. Voyager does not run on sunlight. It is worth saying that plainly, because so many of our machines in space depend on solar panels, those wide dark wings that drink in sunlight and turn it into electricity. Out where Voyager lives, that would be useless. The sun is a distant point of light there, delivering almost no usable energy, and a solar panel would sit dead and dark. So the engineers who built Voyager in the 1970s knew from the start that it would have to carry its own power source, something that would keep working in total darkness, billions of kilometers from any star for decades on end, with no way to ever refuel it. And the solution they chose is one of the most elegant and unnerving pieces of engineering our species has ever flown. Bolted to the side of the spacecraft are 3 devices with a long and clumsy name: radioisotope thermoelectric generators. We can just call them generators, but keep that full name somewhere in the back of your mind, because every piece of it matters. At the core of each one sits a quantity of a very special metal, a form of the element plutonium called plutonium-238. Now, when most people hear the word plutonium, they think of bombs, and it is true that a different form of plutonium is used in weapons. But this form, plutonium-238, cannot be used to make a bomb. It is used for one thing and one thing only, and that thing is warmth. Because plutonium-238 has a remarkable and slightly eerie property. It is radioactive, and as it sits there, doing nothing, touching nothing, connected to nothing, its atoms are quietly coming apart. Let me explain what that actually means, because it is the whole secret of the spacecraft's long life. Every substance is made of atoms, and most atoms are stable. They sit there unchanged for billions of years, content, doing nothing. But some atoms are unstable. They are built slightly wrong, holding a little too much energy inside their cores, and sooner or later each one lets go of a small piece of itself, flinging out a tiny fast-moving fragment and settling into a more comfortable arrangement. This is radioactive decay, And it is not an explosion or a reaction. It is a slow, steady, spontaneous crumbling, atom by atom, entirely on its own schedule. And here is the key. Each time one of those atoms flings out its little fragment, that fragment goes racing off and slams into the surrounding material, and its motion turns into warmth. One atom decaying releases a trace of heat too small to notice. But in a lump of plutonium-238, there are more atoms than you could count in 100 lifetimes, and billions upon billions of them are decaying every second, each one adding its small pulse of warmth to the whole. The result is that the lump gets hot, and stays hot, entirely by itself, with no fire, no fuel, no reaction to start or stop. It simply glows. I mean that almost literally. A quantity of plutonium-238 sitting on a table will grow warm and then hot from its own decay, and a large enough piece glows a soft, steady red, the colour of a dying coal, purely from the heat of its own atoms coming apart. It does not need air. It does not need to be lit. You cannot blow it out. Set it down and walk away, and come back an hour later, a year later, a decade later, and it is still warm, still glowing faintly in the dark, still pouring out heat, as reliably as it did the moment it was made. It is, in the most literal sense, a fire that needs nothing and cannot be extinguished. And that is exactly what the engineers wanted, because a machine bound for the darkness between the stars needs a source of warmth that will never ask for anything and never go out. There is a reason this particular kind of plutonium was chosen, and it comes down to a careful balance. The rate at which a radioactive substance decays determines how much heat it gives off. Something that decays extremely slowly, over millions of years, barely gets warm at all, because so few of its atoms come apart in any given second. Something that decays extremely fast burns itself out in days or weeks, far too quickly to power a decades-long mission. Plutonium-238 sits in a sweet spot between those extremes. It decays quickly enough to pour out a genuinely useful amount of warmth, enough to run a spacecraft, and yet slowly enough that it will keep doing so for the better part of a century. It is, in a sense, tuned for exactly this job, warm enough to matter and patient enough to last. And it is safer than the word plutonium makes it sound. The particles it flings out as it decays are a heavy, slow kind of radiation that can be stopped by almost anything, by a sheet of paper, by the outer layer of your skin, by the sturdy casing the fuel is sealed inside. It is not the penetrating, dangerous radiation people usually imagine. The fuel is also made in a tough ceramic form, closer to a fired pottery than to a raw metal, specifically so that even in an accident it would tend to break into large harmless chunks rather than a fine dust, and so that it could survive extreme conditions without scattering. This same family of power source, this quiet warmth of decaying material, has done more than fly to the outer planets. Smaller versions once kept early cardiac pacemakers running inside people's chests, ticking away for years on the warmth of the atom. The technology that keeps Voyager alive in the dark is the same gentle, reliable idea, scaled up and sent to the edge of the solar system. Not an engine that burns, not a battery that drains in the ordinary way, but a substance that simply cannot stop being warm. Let me put you in the room with it, just once, so you understand what we actually sent into space. Picture a clean, bright laboratory in 1976, a year before launch. On a workbench behind thick shielding and handled only through heavy gloves sits one of the fuel pellets that will go inside Voyager's generators. It is small, about the size of a marshmallow, a dull ceramic lump of plutonium oxide, and it is warm. Not warm like something recently taken from an oven, cooling as you watch. Warm like something that will never cool, not on any timescale that means anything to a human being. Hold your gloved hand near it, and you feel the heat radiating off it, patient and constant. Set it in a dark room and it glows, softly, a small red ember with no flame. There is nothing burning, nothing is plugged in. No reaction is running that anyone started or could stop. Far inside that little pellet, billions of times every second, atoms are quietly splitting and releasing their tiny bursts of warmth, and they have been doing it since before the pellet was shaped, and they will keep doing it, growing only very slowly fainter, for longer than the spacecraft will ever fly. You're looking at a warmth that owes nothing to the world around it, a private, self-sustaining fire small enough to hold in your palm, and this is the moment to notice something that will haunt the rest of this story. That warmth in your gloved hand, That steady red glow that seems so reliable, so eternal, is already fading. Slowly, imperceptibly, but truly. Every atom that decays and gives up its little pulse of heat is an atom that is now spent, that will never decay again. The fire is real, but the fuel is finite. There is a fixed number of those unstable atoms in the pellet, and every warm second uses some of them up and none of them ever come back. The glow you are holding is both a fire and a clock. It is warmth, and it is a countdown, running at the very same time, in the very same object, driven by the very same process. The fire that keeps it warm is the hourglass that measures out its life. Hold that image, because we are going to return to it, and when we do, it will have grown teeth. Now take those hot little pellets and put them to work, and you have the generator. Inside each of Voyager's 3 generators, the plutonium sits at the centre, glowing with its unquenchable warmth, and that warmth does 2 jobs at once. Some of it is turned into electricity, which we will get to shortly, and that electricity runs the computers and the radio and the instruments. But a great deal of that warmth does something simpler and just as vital. It keeps the spacecraft warm. It radiates out through the body of the machine, keeping the electronics from freezing, keeping the fuel lines from turning solid, holding the whole delicate assembly at a temperature where it can still function, in a place hundreds of degrees below zero. The generators are at the same time the spacecraft's power plant and its furnace, its source of electricity and its source of survival, and both of those come from the same simple fact of plutonium quietly falling apart. When Voyager launched in 1977, those 3 generators together produced about 470 watts of electrical power. To give that a shape you can feel, that is roughly enough to run a few bright household light bulbs, or the kind of power a modern desktop computer might draw. It is not much. It never was much. The entire spacecraft, all its systems, all its instruments, its radio calling across the emptiness between the stars, has always run on less electricity than you might use to light a single room. And it has done it, without interruption, without a single refueling for close to half a century, on the strength of a substance that simply refuses to stop being warm. So there it is, the fire Voyager carries, the reason it has not frozen. Not sunlight, not a battery in any ordinary sense. A small self-contained furnace of decaying plutonium, glowing quietly at the centre of the machine, asking nothing of the darkness, giving warmth freely and slowly and visibly, spending itself as it does. But I've skipped over something. I told you the generator turned some of that warmth into electricity, and I said it as though that were a simple thing. It is not a simple thing at all. Turning heat directly into electricity, with no moving parts, nothing spinning, nothing burning, in a sealed box that has to work untouched for 50 years, is its own small miracle of physics, and the way it works contains a beautiful and slightly cruel irony that sits right at the centre of why Voyager both lives and dies. Let me show you the engine inside the furnace. Part 6. The engine with no moving parts. Think about how we usually make electricity. Almost every method we have ever devised comes down to the same basic trick. Make something spin. In a coal or gas plant, we burn fuel to boil water into steam, and the steam pushes a turbine that spins a magnet inside a coil of wire, and that spinning makes electricity. In a hydroelectric dam, falling water spins the turbine. In a wind farm, the wind does it. Even in a nuclear power plant, all that exotic physics is really just a very sophisticated way of boiling water to spin a turbine. Spinning, always spinning, and spinning means moving parts, and moving parts means bearings that wear, blades that fatigue, seals that fail, machinery that needs maintenance and eventually breaks down. You could never send a spinning turbine into the space between the stars and expect it to run untouched for 50 years. It would seize, or wear out, or shake itself apart long before the job was done. So Voyager's generators do something completely different, something with no spinning at all, no turbine, no piston, nothing that moves. They turn heat directly into electricity using a quiet piece of physics called the thermoelectric effect. And the principle behind it is surprisingly simple to state. If you take certain special materials and you make one end of them hot while keeping the other end cold, that difference in temperature, all by itself, will push an electric current through the material. Not by spinning anything, just from the temperature difference itself. Heat on one side, cold on the other, and electricity flows through the middle. Hold that in your mind because it is genuinely strange when you sit with it. The mere fact of one side being hotter than the other becomes a flow of electrical power, with nothing moving that you could ever see. Why does that happen? You can picture it, loosely, like this. Inside those special materials are countless tiny charged particles, the same particles whose flow we call electricity. When one end of the material is heated, the particles at the hot end become more energetic and agitated, jostling harder, moving faster, while the particles at the cold end stay sluggish and calm. And just as a crowd will naturally spread out from a packed, frantic corner toward an emptier, calmer one, those energetic particles tend to drift from the hot end toward the cold end, spreading out, seeking balance. That drift of charged particles, all flowing the same direction, from hot toward cold, is an electric current. As long as you keep one side hot and the other side cold, the drift continues and the current keeps flowing. Let the two ends reach the same temperature and the drift stops, and so does the power. The whole thing runs on the difference, on the gap between hot and cold. Now you can see why this was the perfect choice for Voyager, because the spacecraft has exactly what this trick requires, and it has it for free. At the center of each generator sits the plutonium, glowing with the intense warmth of its own decay, providing the hot side. And on the outside of each generator are fins that face out into the emptiness of space, radiating heat away and staying cold, providing the cold side. The plutonium keeps the inside hot, space keeps the outside cold. And across the gap between them, hundreds of degrees of temperature difference, the current quietly flows, with nothing moving, nothing wearing out, nothing to break. It is a nuclear power plant in the most literal sense, heat in one side and electricity out the other, sealed, silent, and solid as a stone. This is a large part of why a machine from the 1970s is still running today. There was never a spinning part inside it to fail. There was only a temperature difference patiently doing its work for decade after decade. Think about what an achievement of reliability that is. We are surrounded in our daily lives by machines that break. Cars need constant service. Appliances wear out and get replaced. The average piece of technology in your home would be lucky to run untouched for 10 years. And here is a power source that has run continuously for close to 50, in an environment of brutal cold and constant radiation, with no maintenance, no repairs, no replacement parts, no human hand ever laid on it again after launch. The reason it can do that is precisely because it does nothing. It does not spin, does not pump, does not cycle, does not move at all. It has no bearings to grind down, no blades to crack, no seals to leak, no fluid to circulate. It just sits there, hot on the inside, cold on the outside, and lets the flow of warmth become a flow of electricity, as quietly and reliably as a stone sits on the ground. There is a lesson buried in that, about how the most durable machines are often the ones with the fewest ways to fail, but the point for us is simpler. This is why Voyager is still awake. Its fire cannot go out, and the engine that draws power from that fire has no parts that can wear away. This same quiet method has powered nearly every mission we have ever sent into the far reaches of the solar system, all the places too dark and too distant for sunlight to help. The craft that explored the outer planets, the ones that landed on distant worlds and roved across cold red deserts, the probe that flew past the most remote objects we have ever visited, so many of them have relied on this same trick. A warm lump of decaying material, and a set of thermocouples turning that warmth into a lifeline of electricity. It is one of the great unsung technologies of exploration, the humble, patient power source that has quietly kept our machines alive wherever the sun could not reach. And on Voyager, it has done its job longer than anywhere else, longer than its makers ever imagined it could. But here is where the story turns, and where a beautiful irony reveals itself, one that sits right at the center of everything. This method of making electricity, this elegant, unbreakable, no-moving parts method, is also spectacularly inefficient. Of all the warmth pouring out of the plutonium, only a small fraction, something like 6 or 7% of it, actually gets turned into electricity. The rest, the other 90-odd%, does not become power at all. It just flows on through the generator and out into space as plain heat, seemingly wasted, poured away into the dark. If you were an engineer trying to build the most efficient possible power source, you would be horrified. You're throwing away more than 9/10 of your energy. By the standards of a power plant, it is a disaster. Except it is not a disaster at all. It is the second reason Voyager is still alive. Because remember what the spacecraft actually needs, out there in the emptiness. It needs electricity, yes, to run its systems, but just as urgently, it needs warmth to keep itself from freezing solid. And all that so-called waste heat, the 90% that does not become electricity, is not wasted at all. It is the very thing keeping the spacecraft warm. It flows through the body of the machine, warming the electronics, warming the fuel lines, holding the whole delicate assembly at a livable temperature in a place hundreds of degrees below zero. The inefficiency that would horrify a power engineer is the exact thing that saves the spacecraft's life. What looks like waste is actually survival. If the generators were more efficient, if they turned more of that heat into electricity and let less escape as warmth, Voyager might have more power, but it would also be colder, more likely to freeze, more likely to have died long ago. The machine lives precisely because it is bad at converting heat, because it spills warmth everywhere, because it is, by the numbers, a leaky and wasteful little furnace. I find something almost tender in that, and I want to sit with it for a moment. We tend to think of waste as failure, of inefficiency as a flaw to be engineered away. But out there in the endless cold, the wasteful warmth is the thing that matters most. The spacecraft survives not despite spilling most of its energy as heat, but because of it. It is kept alive by its own imperfection, warmed by the very energy it fails to use. There is a small lesson in that, maybe, about how the things we dismiss as waste and loss are sometimes quietly holding everything together. But I will let you find your own meaning there. The physics is what it is. A furnace that keeps a machine alive across half a century of night by being gloriously, life-savingly bad at its official job. So now we have the full picture of why Voyager has not frozen. It carries a small furnace of decaying plutonium that makes warmth all on its own, needing nothing from the universe around it. That warmth is turned partly into the trickle of electricity that runs the machine, and mostly into the flood of heat that keeps it from freezing, and it all sits inside the perfect insulation of empty space, which cannot easily steal that warmth away, and can only wait for the spacecraft to slowly radiate it into the dark. Fire on the inside, insulation all around, a balance held for 49 years. It is a genuinely lovely piece of engineering, and if the story ended there, it would be a story of pure triumph. But the story does not end there, because I have been telling you, from the very beginning, that the thing keeping Voyager alive is the same thing killing it. And now that you understand the furnace, now that you see how completely the spacecraft depends on that quiet plutonium warmth, you are finally ready to understand the terror hiding inside it. The fire has a flaw that no engineering can fix, a flaw written into the very atoms it is made of. It is fading. It has been fading since before it launched, and it fades on a schedule so precise, so unbreakable, that you could have calculated the hour of the spacecraft's death on the day it was built. That schedule has a name, and it is the coldest, most honest clock in all of physics. It is time to look at the number that dooms Voyager, and to understand why it cannot be argued with, slowed down, or stopped. Part 7. The clock that cannot be reset. The number that dooms Voyager is not dramatic to look at. It is not a countdown ticking on a screen, not a warning light, not an alarm. It is a quiet, ordinary-looking figure that you could walk past 1,000 times without feeling its weight. The number is 87.7 years. That is what physicists call the half-life of plutonium-238. And once you understand what a half-life is, you will understand why the spacecraft's death was sealed before it ever left the launch pad. Here is what a half-life means. Remember that the plutonium makes its warmth by slowly decaying, atom by atom, each unstable atom eventually flinging out a fragment of itself and going quiet forever. That decay does not happen all at once, and it does not happen at a steady, unchanging pace forever. It happens in a very particular rhythm. The half-life is the amount of time it takes for half of the atoms in a sample to decay away. So for plutonium-238, if you start with a certain amount today, then 87.7 years from now, half of it will have decayed, and only half will remain. And because it is only half that remains, it is now producing only about half as much warmth as it did at the start. Wait another 87.7 years, and half of what was left decays too, leaving you a quarter of the original, making a quarter of the warmth. The fire does not go out suddenly. It fades, steadily, halving and halving, growing gentler every year, on a schedule set by the deepest rules of the atom, and that schedule cannot be changed. This is the part I need you to feel, because it is the true source of the dread in this story. There is nothing anyone can do, anywhere, by any means, to speed up or slow down that decay. You cannot warm the plutonium to make it decay faster, or cool it to make it decay slower. You cannot press on it, or shield it, or plead with it. The rate is fixed by the internal structure of the atom itself, one of the most unbreakable constants in all of nature. The plutonium in Voyager has been decaying at exactly the same relentless pace since the moment it was made, and it will keep decaying at that same pace until it is gone, utterly indifferent to the spacecraft's journey, to the engineers' hopes, to anything that happens. It is the most honest clock there is, because it cannot be bribed, cannot be reset, and cannot be stopped. It simply counts and counts and counts. There is a particular cruelty in the shape of this decline, and it is worth understanding, because it is not a straight line. When something fades by halves, it does not lose the same amount each year. It loses a fraction of whatever is left. Early on, when there is a lot of fuel, even a small fraction is a large amount of warmth, and the losses feel manageable. But the decline never stops, and it works on an ever-shrinking base, so that every watt becomes harder to spare than the one before it. The spacecraft is not coasting gently downhill toward a distant end. It is descending a slope that, in the ways that matter most, grows steeper underfoot as the margins thin, each remaining watt more precious and more fought over than the last. The engineers are not managing a comfortable surplus that will last a while longer. They are managing a shortage that deepens every single year. And there is a second thief working alongside the first, which makes the real decline even faster than the plutonium alone would explain. Remember that the warmth is turned into electricity by those special materials, the thermocouples, sitting for decades right against the intense heat of the fuel. Nothing survives that kind of relentless baking unchanged. Over the years, the thermocouples themselves degrade, slowly losing their ability to convert heat into current, so that even the warmth that remains is turned into electricity less and less efficiently. So the spacecraft loses on both ends at once. It has less warmth to work with, because the fuel is fading, and it converts that dwindling warmth into power less effectively, because the converter is wearing out. Two independent forms of decay, the fuel and the engine that uses it, both moving in the same direction, both irreversible, both compounding. From about 470 watts at launch to somewhere near 249 watts today, the machine has quietly given up half of its strength, and it will keep giving up more every year, with no bottom until the fire is too faint to matter at all. Let me translate 4 watts a year into something you can feel. 4 watts is almost nothing, less than the power drawn by the small light that glows on a phone charger. It is a loss so tiny that in any single year you could easily ignore it. But it never stops, and it never reverses, and it lands on a machine that never had much power to begin with. The whole spacecraft, remember, launched with only about the strength of a few light bulbs, and it has already lost half of that. So 4 watts a year is not a rounding error to Voyager. It is the steady, patient subtraction that is slowly closing the whole mission down. It is the reason instruments get switched off, the reason heaters go dark, the reason every year brings a new and harder decision about what to give up. And it is completely indifferent to how badly anyone wants it to stop. The plutonium does not know the mission is precious. It does not know anyone is listening. It simply decays at exactly the rate it has always decayed, taking its small toll year after year, and no amount of care or cleverness on Earth can add a single watt back. This is what it truly means to live on a fixed and fading store of warmth. Every year you are a little poorer than the year before, there is no way to earn more, and the only choice left to you is how wisely to spend what still remains. You can see the counting in the numbers if you follow the spacecraft's power over the years. At launch, in 1977, the 3 generators produced about 470 watts of electricity. Today, in 2026, they produce somewhere around 249 watts. In the decades between, the spacecraft has lost roughly half of its electrical power, almost exactly what the half-life would predict, fading away just as the physics said it would. Every single year, the generators produce about 4 watts less than the year before. 4 watts, gone, every year, and never coming back. And that loss comes from 2 things happening at once, both of them irreversible. The plutonium is slowly fading, as we have seen, And on top of that, the delicate materials that convert the heat to electricity, sitting for decades right beside that intense warmth, are themselves slowly wearing out, becoming a little less able to do their job each year. So the decline is even steeper than the plutonium alone would cause. The fuel fades, and the engine that uses it wears down, and both of them only ever move in one direction. There is no refilling it. I want to be completely clear about this, because it is the wall that every hope runs into. You cannot add more plutonium. There is no way to reach the spacecraft, no crew that could carry fuel to it, and even here on Earth, this particular kind of plutonium is so difficult and so expensive to produce that its scarcity limits how many missions we can send into the outer darkness at all. There is no rescue ship because Voyager is fleeing outward at 17 kilometers per second, and even our fastest spacecraft could not catch it and match its speed within a human lifetime. And you cannot even help it by adding warmth from outside, because adding warmth would mean adding power, and power is the very thing running out. The most advanced spacefaring civilization on its home planet, capable of rewriting the spacecraft's memory from a day and a half away, can do absolutely nothing to give it one more atom of fuel. All anyone can do is help it spend, as wisely as possible, the finite warmth it already carries. Now let me say the thing this has all been building toward, and let me say it slowly, because it deserves to be felt rather than rushed past. Voyager's ending was written at its beginning. On the day it launched, in 1977, when its engineers were young and the mission was new and everything lay ahead, the plutonium was already years into its decay. The clock was already running. It had been running since the fuel was made, before the spacecraft was even assembled. Every triumph the mission has ever had, every planet it visited, every record it broke, every heroic repair that pulled it back from silence, happened while that clock kept ticking, unmoved and unimpressed. None of it bought the spacecraft a single extra atom of fuel. None of it added a single hour to the fundamental countdown. The machine has been dying, quietly and precisely, the entire time it has been alive, and the dying and the living have been the exact same process from the very first day. This is the terror at the centre of the title, if you want to call it terror. The reason Voyager refuses to die is that it carries a fire that needs nothing from the universe, a self-sustaining warmth that no cold and no emptiness can take from it by force. But that same fire, by the unbreakable law of the half-life, is fading on a schedule fixed before launch and impossible to change. The thing that frees the spacecraft from every outside threat is the thing that dooms it from within. Its independence is its sentence. It cannot be killed by the cold, cannot be killed by the emptiness, cannot be killed by anything out there in the dark, and so instead it is being killed, gently and certainly, by the very warmth that keeps it alive. The fire and the hourglass are one object. To burn is to be spent. There was never a version of this story where the warmth lasted forever, because the warmth and the fuel were always the same finite thing. And yet, I do not think this is only a sad fact, and I want to be careful here, because there is something in it that is closer to the truth of all things than to mere grief. Everything that is warm is running down. Every fire spends its fuel. Every star, including our own sun, is burning through a finite store of energy and will one day fade, and so, in its own way, is everything alive. Voyager is not exempt from a cruel exception to the universe's rules. Voyager is a small, clear, honest example of the universe's most basic rule, made visible. We took a fire, and we sent it as far into the dark as we possibly could, precisely so that we could watch how long a made thing can hold its warmth against a cold with no edges. And the answer, so far, is nearly 50 years, and counting, which is a very long time for a small fire to burn alone in the dark. The countdown is real. But so is the burning, and the burning has lasted and reached far beyond anything its makers dared to expect. So the fuel is fading, 4 watts a year, on a clock no one can touch. That much is fixed. But knowing the fire is finite only raises the next question, the practical and heartbreaking one. As the warmth slowly drains away, what actually fails first? What is the weak point? The specific thing that the fading fire can no longer protect, the place where the cold finally gets its foot in the door? The answer is smaller and stranger than you might think. It is not the computers. It is not the radio. It comes down in the end to a thin line of liquid, and whether it stays liquid or turns to ice. And that thin line is where the word frozen finally becomes real. Part 8. the freezing line. When people ask whether Voyager will freeze, they usually picture the whole spacecraft turning into a solid block of ice, the entire machine crusted over and lifeless. But that is not how it would happen, and it is not what the engineers are actually afraid of. The real danger is far more specific and far more fragile than a total freeze. It comes down to a thin thread of liquid running through the body of the spacecraft, and the whole survival of the mission may ultimately hinge on whether that one thread stays liquid or turns to ice. To understand why, you have to know how Voyager keeps itself pointed at Earth. Out in the emptiness, the spacecraft has to hold its big dish antenna aimed precisely back at our planet, or its whisper of a signal sails off into the dark and never reaches us. But things drift in space. Tiny forces nudge the spacecraft, and left alone it would slowly turn away from home. So Voyager corrects itself, constantly, using small thrusters, little jets that fire brief puffs to nudge its orientation back into place. And those thrusters run on a liquid fuel called hydrazine, stored in a tank and carried to the jets through thin pipes, fuel lines threading through the structure of the spacecraft like veins. Here is the vulnerability. Hydrazine freezes at a temperature only a little below room temperature, at about 2 degrees on the Celsius scale, which is just a few degrees above the freezing point of water. That is not cold at all by the standards of space. The emptiness Voyager flies through is hundreds of degrees colder than that. So those fuel lines, carrying a liquid that turns solid at nearly room temperature, are running through the frigid outer body of a spacecraft surrounded by a cold that would freeze the fuel in an instant if it ever reached it. The only thing keeping that hydrazine liquid, the only thing standing between the fuel and a killing freeze, is warmth. Warmth from the generators, that flood of so-called waste heat we talked about, and warmth from small electric heaters placed near the critical lines. As long as enough heat reaches those pipes, the fuel stays liquid, the thrusters keep working, the antenna stays pointed at Earth, and the conversation continues. But now recall what is happening to the spacecraft's warmth. It is fading. 4 watts a year, gone and never returning, as the plutonium decays and the generators wear down. And that means every year there is a little less heat available to go around, and every watt of it becomes more precious. The engineers face an impossible arithmetic. The heaters that keep the fuel lines warm draw power, and power is the thing running out. So they are forced, slowly, to let things get colder, to shut off heaters they can no longer afford, and to watch the temperature in those fuel lines creep downward, degree by degree, toward the point where the hydrazine would freeze. This is the knife edge the whole mission now balances on. Not a sudden freeze from the hostile dark, but a slow, managed cooling from within, as the fading fire is stretched thinner and thinner across everything it has to keep warm. And this is the precise answer to the question on the thumbnail. The question you may have clicked on almost as a joke. Why has Voyager not frozen? It has not frozen because, for now, a shrinking budget of warmth is still being spent, with extraordinary care, to keep a few critical lines of fuel just a few degrees above the temperature at which they would turn to ice. The engineers track the temperature of that propellant closely, and they hold it above a carefully chosen limit, a line they will not let it cross, fighting for every fraction of a degree. The survival of the most distant machine in human history comes down, in the end, to keeping a little tube of liquid from freezing in the dark. That is the whole of it. Not the computers, not the radio, not the ground systems. A thin line of fuel, and whether it stays warm enough to flow. The engineers do not leave this to chance, and the way they watch over it tells you how serious it is. They have set a temperature limit for that propellant, a line they have decided the fuel must never be allowed to fall below, a floor with a safety margin built in above the actual freezing point. And they monitor the temperature of those lines from across the solar system, watching the numbers arrive a day late, and they manage the spacecraft's precious warmth to keep the fuel above that floor, no matter what else has to be sacrificed. It has become one of the central tasks of the whole mission. This constant, careful guarding of a temperature, this refusal to let a thin thread of liquid slip into ice. Everything else the spacecraft does, every measurement it takes, every signal it sends, depends first on this quiet, unglamorous vigil over whether the fuel can still flow, and it grows harder every year because of everything we have already seen. The warmth that keeps the fuel liquid comes from the same fading fire that runs everything else, and that fire is dimming 4 watts a year on the clock that cannot be reset. So the margin above the freezing line thins over time. The heaters that warm the fuel draw power the spacecraft can barely spare, and so the engineers are forced into an agonizing trade, weighing every heater against every other need, letting some parts of the machine grow dangerously cold in order to keep the critical lines just warm enough. It is like tending a fire on a freezing night with a dwindling pile of wood, deciding which corners of the room you will let go cold so that the one corner that matters most can stay warm a little longer. Except the night is 50 years long, the wood cannot be replenished, and the person tending the fire is doing it blind from 16 billion miles away, learning the result of every choice a day and a half after they make it. That is the real meaning of the question, why has it not frozen? It has not frozen because, for now, that impossible fire tending is still succeeding, one careful degree at a time. Let me take you to that line, because I think you should see the place where the mission actually lives or dies. Imagine you could shrink down and travel along one of those fuel lines, following the hydrazine through the body of the spacecraft. You begin near the center, where the generators glow with their fading warmth, and here the fuel is comfortable, kept liquid by the heat radiating off the plutonium. But then follow the line outward, away from that central warmth, toward the edges of the machine where the thrusters wait. As you go, it gets colder. The warmth of the generators falls away behind you, and the terrible chill of the surrounding emptiness presses in from every side, held back only by thin insulation and the faint help of a small electric heater somewhere nearby. Here, near the outer edge, the fuel is only barely liquid, its temperature hovering a few degrees above the point where it would begin to thicken, and then to slush, and then to freeze solid. You're standing at the actual frontier of the mission, the boundary between a spacecraft that can still turn to face home and one that cannot. And every year, as the fire fades, that frontier creeps a little further inward, the cold advancing a little closer to the warm center, the safe zone shrinking around the shrinking fire. The whole of Voyager's future is written in the temperature of this one thin line, and whether the warmth reaching it will hold, one more year, and then one more after that. If that fuel ever does freeze, the ending is quiet but final. The thrusters would no longer be able to fire. The spacecraft would slowly drift off its careful aim, its dish antenna turning gradually away from the small blue world it has been facing for half a century, until its whisper no longer reached us at all. It would not die in that moment. It might still be warm in its center, its computers might still be running, its radio might still be calling, but it would be calling in the wrong direction, into empty space, with no way to turn back toward home. A living machine still trying to speak that could no longer aim its voice. There is something almost unbearably lonely in that image, a spacecraft not silenced by death but by the simple inability to point itself the right way, and it is one of the several ends the engineers are working to hold off for as long as the warmth allows. So the fuel line has to stay warm, and the warmth is fading, and the two facts are closing slowly toward each other like a vice, which forces a hard and painful strategy, the only one available. If the fire can no longer keep everything warm and everything running, then the engineers must choose what to keep and what to let go. They must begin, deliberately, to shut parts of the spacecraft down, switching off system after system, sacrificing pieces of the machine to keep the most essential pieces alive a little longer. It is a slow retreat, a careful surrender of one thing after another, all to protect that thin warm line of fuel and the fading voice it makes possible. And the way they are doing it, the order in which a spacecraft is asked to give up its own parts to survive, is one of the most quietly moving things in the entire story. Let me show you what it looks like to keep something alive by turning it off, one light at a time. Part 9. Turning off the lights to stay alive. There is a strange and gentle logic to keeping Voyager alive now, and it runs exactly opposite to how we usually think about survival. We tend to imagine survival as holding on to everything, gripping tight, losing nothing. But for a spacecraft with a slowly fading fire, survival means the opposite. It means letting go. It means choosing, deliberately, what to switch off, so that whatever remains can keep running a little longer on the warmth that is left. To keep Voyager alive, the engineers have had to spend years turning it off, one piece at a time. Think again about the arithmetic they face. The power fades by about 4 watts every year, and every system on the spacecraft draws some of that power and produces or requires some of that warmth. When there is no longer enough to run everything, something has to give. So the mission has become a long, careful retreat, a slow surrender of one capability after another, each sacrifice buying a little more time for what is kept. It began long ago, The cameras that took Voyager's famous photographs were switched off decades back. Once the spacecraft had travelled beyond anything left to photograph, their power saved for more essential things. Various heaters have been shut down over the years, letting parts of the spacecraft grow colder to keep other parts warm, and more recently the sacrifices have reached the scientific instruments themselves, the very tools that make Voyager not just a survivor, but an explorer, still sending back real measurements from a place nothing else has ever been. The instruments have been going dark one by one. Each one that is switched off is a small, permanent loss, a sense the spacecraft will never have again, and each one is chosen with great care, weighed against how much power it draws and how much science it still returns. In April of 2026, the engineers switched off an instrument on Voyager, one that had been measuring charged particles, the low-energy charged particle detector, in order to save power. That shutdown left the spacecraft with only 2 of its scientific instruments still operating, just 2 sensors remaining out of the full suite it launched with, still faithfully measuring the space around it and sending the results home across the emptiness. 2 instruments, where once there were many, and in time, those 2 will have to be switched off as well, when the fire fades too far to run even them. Consider what each of those instruments actually is, so you feel the cost of switching one off. These are not luxuries. Each one is a sense, a way the spacecraft feels the space around it, measuring the magnetic fields, the charged particles, the faint waves rippling through the near-empty medium between the stars. And Voyager is not measuring these things somewhere we can easily study another way. It is measuring them from inside interstellar space itself, from a place no other machine built by humans has ever reached, sampling directly the conditions beyond the sun's protective bubble. When one of those instruments is switched off, we do not just lose a piece of hardware. We lose a stream of information from a location we will not visit again for a very long time, perhaps not in the lifetime of anyone alive today. Each shutdown is a small, permanent narrowing of the only direct window we have into that region, a sense going dark forever, and the engineers weigh each one with the gravity it deserves. And there is that quiet, stubborn detail I keep returning to, because it moves me every time. Again and again, as the engineers are forced to let the spacecraft grow colder than it was ever meant to be, colder than anyone tested it for back when it was built, the old machine simply endures it. Parts that should stop working at such temperatures keep working. Fuel that might be expected to thicken and fail holds on. Voyager keeps turning out to be quietly tougher than its own specifications, tougher than the careful, cautious paperwork its makers wrote in the 1970s. It is as though the machine had been given secret reserves its builders did not know they had included, hidden margins of endurance, and now, at the end of its life, it is spending every last one of them, holding on in conditions that should have finished it, exceeding the expectations of the very people who made it and who are now gently letting it go. There is a detail in all of this that I find genuinely moving, and it says something surprising about the old machine. As the engineers have been forced to let parts of the spacecraft grow colder than they were ever designed to be, colder than anyone tested them for back in the 1970s, they keep discovering that the spacecraft endures it anyway. Components that should, by their own specifications, have stopped working at such low temperatures keep working regardless. Fuel that might have been expected to freeze holds on. The old machine, again and again, turns out to be quietly tougher than its own paperwork ever claimed, surviving in conditions its builders would have said were beyond it. It is as though Voyager, having been given a finite life and a fading fire, has decided to spend every last margin its makers accidentally built into it, holding on in the cold longer than it has any right to, exceeding the expectations of the very people who made it. But toughness only stretches the timeline, it does not change the ending. The engineers have a plan, and the plan is honest about what is coming. They hope to keep at least one scientific instrument running into the early 2030s, so that Voyager remains, right up until nearly the end, not just a beacon but an explorer, still learning something new about the space between the stars, and after the last instrument goes dark, they hope to keep the spacecraft sending back at least its basic engineering data, its own heartbeat and health, its simple signal that says I'm still here, perhaps as late as 2036. Around that time, the power is expected to finally fall below the level needed to send any signal at all, and then the conversation, the one that has lasted since 1977, will come to its end. I want you to notice what kind of dying this is, because it is not the dying we usually imagine for a machine. It is not a sudden failure, a dramatic breakdown, a violent end. It is a slow, dignified powering down, a careful and deliberate letting go, managed with tenderness by the people who tend it. Piece by piece, the spacecraft is asked to give up its senses, to go quiet in one way and then another, also that its central warmth and its faint voice can last a little longer. It is being helped to die slowly, on its own terms, rather than allowed to fail all at once. There is a word for that kind of care when it is given to the living, and I think it is not too much to use it here. This is something close to hospice, carried out across 16 billion miles, for a machine that has travelled farther and lasted longer than anything else we have ever made. And the people doing it know exactly what they are doing. They are not fooling themselves that the spacecraft can be saved, because it cannot be, not against the half-life clock. They are simply making sure that the ending, when it comes, is as long and as graceful and as full of discovery as the fading fire will allow. Every instrument they keep alive one more year is a gift of a few more measurements from a place we will not visit again in any of our lifetimes. Every watt they manage carefully is a little more time for the voice to keep arriving. They are stewards of a small, precious warmth, spending it wisely, refusing to waste a single watt, refusing to let the machine go dark one day sooner than it has to. So that is where the mission stands. A fading fire, a shrinking budget of warmth, a spacecraft going quiet 1 sense at a time, tended by people determined to make the long goodbye last. We have seen why it is not frozen, the private fire and the insulating emptiness. We have seen why it is dying anyway, the unbreakable half-life clock. We have seen the thin line of fuel where survival actually lives, and the careful surrender that keeps that line warm. Now it is time to draw all of it together, to hold the whole strange truth in a single view, and to finally answer, fully, the question that has been running underneath this entire story. Not just why is it not frozen, and not just why is it dying, but the deeper thing that joins them. Why, out of everything we have ever built, does this one small machine so stubbornly refuse to die? Part 10. Why it refuses to die. So let us finally answer it, the whole question, all at once. Why does Voyager 1 refuse to die? It refuses to die because of a rare and beautiful independence. Almost everything else we send into space depends on something outside itself. Satellites near Earth depend on sunlight for their solar panels. Rovers depend on the mission teams that drive them and the daylight that powers them. But Voyager, from the beginning, was built to depend on nothing. Its warmth comes from within, from a fire that needs no air, no fuel deliveries, no sunlight, no help of any kind, a fire that simply burns on the strength of matter falling apart. And the emptiness it flies through, far from being its enemy, turns out to be its insulation, unable to steal that warmth away by force, able only to wait. A self-contained fire, wrapped in the perfect insulation of nothing, asking the universe for nothing at all. That is why the cold cannot kill it. That is why it holds on. And there is a second reason, and it is not made of physics. It is made of people. The spacecraft refuses to die because a small group of human beings refuses to let it, and their refusal is its own kind of fire. When its memory failed, they rewrote its mind from a day and a half away. When its thrusters clogged, they resurrected a set that had been dead for 20 years. When its power fades, they choose, with great care, what to switch off so the rest can live. The machine's stubbornness and the steward's devotion have become a single thing, one warmth on the spacecraft and another warmth in the people who tend it, both of them refusing year after year to let the dark simply win. Voyager keeps living because it was built to need nothing, and because it is loved by people who give it everything they can across an impossible distance. But now hold that triumph up against the other truth, the one we have carried since the beginning, and feel the two of them together. Because the very independence that makes Voyager unkillable is also exactly what dooms it. The fire that needs nothing from the universe is the fire that can never be refilled by anything in the universe. Its freedom from the cold is purchased by its dependence on a finite store of warmth that only ever shrinks. It cannot be killed from outside, and so it is being killed from within by the same steady decay that gives it life. Remember the pellet glowing in the gloved hand, the warmth that was also a countdown. That image has grown its teeth now. The fire is the hourglass. To burn is to be spent. Every warm moment that keeps the spacecraft alive is a moment subtracted from the total it was given, and there is no adding to that total, ever. The reason it refuses to die is precisely the reason it must. Its life and its death are not opposites. They are the same fire seen from two sides. That is the terror in the title, if terror is even the right word, and I have come to think it is not quite. There is nothing here that threatens you, or the earth, or anyone. The word terrifying in the ordinary sense does not really fit a small warm machine glowing quietly in the dark 16 billion miles from anyone. What is actually unsettling about it is something more intimate than fear. It is recognition. Because Voyager is not an exception to the universe's rules. It is one of the clearest examples of them we have ever made. It runs on a fire it did not light and cannot refill. It survives on borrowed warmth in an indifferent dark. It holds on with everything it has, tended by people who love it, and it is running down anyway, gently, precisely, on a clock that started before it began. And if that description makes something turn over quietly in your chest, it may be because it is not only a description of a spacecraft. It is, in its shape, a description of every warm and living thing there has ever been, including the one listening to this right now. This is why, I think, the story of Voyager reaches people who have never cared about spacecraft at all. On the surface, it is a tale about engineering, about watts and thermocouples and fuel lines. But underneath, it is telling us something we already know in our bodies and rarely say out loud. Everything warm is temporary. Everything that glows is spending itself to do it. The sun overhead, pouring out the light that grew every living thing on Earth, is burning through a finite store of fuel and will one day fade. The stars scattered across the night sky are each a fire on its own countdown, and you, lying there in the warmth of your own body, are a small fire too, running on energy borrowed from the world, unable to store it forever, holding your warmth against the same patient cold that waits for everything. We do not usually think about this, and we probably should not think about it too much. But there is a strange comfort in seeing it laid out clearly in something outside ourselves, in a small brave machine at the edge of everything, doing openly and visibly what all warm things do quietly. Voyager is not frightening because it is dying. It is moving because it is dying the way we all are, and holding on the way we all do and reaching out the whole time for home. And the people who tend it are living the same truth from the other side. They are growing older alongside the machine, some of them, spending years of their one finite life keeping this distant thing warm and speaking. When the last signal finally fades, they will grieve it, this object they never touched, and their grief will be real, and it will be the grief of warm things saying goodbye to a warmth they loved. There is nothing foolish in that. To care for something you cannot save, to make its ending as long and as graceful as you can precisely because you know it is ending, is not a waste of devotion. It may be the truest form devotion takes. I said this story was really about people, and here at the centre of it that becomes most true. Consider that the machine and the humans who tend it are dying together, in a sense, on parallel clocks. The engineers who built Voyager have mostly retired or passed away. The ones who keep it alive now are, many of them, growing older alongside it, reading the notes of colleagues who are gone, carrying forward a promise made half a century ago by people they never met. There will come a day, perhaps around 2036, when the last signal fades below the threshold of hearing, and the spacecraft goes silent, and the long mission ends. And some of the people in that room will have spent the better part of their working lives on this one machine, and will have to say goodbye to it. This distant thing they never touched and never saw, that they nonetheless kept alive with their own care for decades. It is a strange and tender kind of grief to mourn a machine, but I do not think it is a foolish one. To keep something warm and speaking against the whole weight of an indifferent universe, for as long as you possibly can, and then to let it go with dignity when you must, may be one of the most human things we have ever done. And so the refusal to die is not really a refusal at all in the end. It is something better than that. It is a holding on for as long as holding on is possible, and a letting go when it is not, and a determination to make the whole span of it, the warmth and the fading both, last and reach as far as it possibly can. Voyager will die. That was never in question, from the first day. What was never guaranteed, what still amazes the people who made it, is that it has lived this long, spoken this far, held its small warmth against this much dark for this many years. The countdown was always running. The wonder is how much life has happened while it ran. There is one part of the story left, and it is the quietest part, and in some ways the most beautiful. We have followed Voyager to the edge of its life, watched the fire fade and the sensors go dark one by one. But the fire fading is not quite the end of the machine. When the last warmth finally drops below the level needed to speak, and the voice goes silent for good, the spacecraft does not stop. It keeps moving. It keeps drifting outward, cooling slowly toward the temperature of the emptiness around it, carrying its message into a dark that will never warm it again. There is a strange peace in what happens to Voyager after it can no longer say "I'm still here," and it is worth sitting with, gently, before we let it go. Let me tell you about the long cold after. Part 11. The long cold after. Sometime in the next decade or so, most likely around 2036, the last signal will come. It will not be dramatic. There will be no final message, no farewell, because the spacecraft does not know it is saying goodbye. It will simply be that one day a faint transmission arrives at the great dishes on Earth, carrying the spacecraft's basic heartbeat, its simple report that it is warm and functioning, and then, after that, the next expected signal will be a little too weak to read, and the one after that weaker still, until there is nothing left to catch. The power will have fallen below the level needed to speak. The fire will have faded past the point where it can push a voice across 16 billion miles, and the long conversation that began in 1977, the one that outlasted careers and outlasted lifetimes, will quietly end. Let me take you to that moment, the last one, because I think it deserves to be witnessed rather than just described. Imagine you're out there beside the spacecraft when it happens. It is not a death you would even see. There is no spark, no shudder, no light going out. The machine is still whole, still drifting, its dish still held patiently toward a pale blue point of light impossibly far behind it. Inside, the fire still glows, only fainter now, too faint to run the radio, but not yet gone. The spacecraft is still warm. It is simply, for the first time in nearly 60 years, no longer speaking. Somewhere behind it, at the end of a signal that takes most of a day to travel, there are people waiting for a voice that does not come, listening to a silence where "I am still here" used to be. The phrase that carried across all those years, "still here, still here, still here," finally does not arrive, not because the machine has stopped, but because the fire can no longer lift the words, and the people listening will know, in that long quiet, that the small warmth they tended for so long has slipped at last below their reach. But here is the part that turns grief towards something gentler. The spacecraft does not stop. The moment it goes silent is not the moment it ends. It keeps moving, exactly as it has for half a century, outward, at 17 kilometers per second, carried by the momentum it gathered from the giant planets long ago and never lost, because the emptiness has nothing to slow it with. It sails on into the space between the stars, still warm at first, its fire fading but not yet out, and over the years that follow, that warmth finally does what the emptiness always waited for it to do. It radiates away, slowly, into the dark, the last of the heat glowing off into the cold with no edges. And now, at the very end, that same cold that could never take the spacecraft's warmth by force receives it at last, gently, by patience, as the fire it could not steal simply gives itself up. The indifferent dark that would not attack the warmth now quietly accepts it, degree by degree, until the machine reaches the temperature of the emptiness around it, and holds there, a cold thing among cold things, at rest in the long quiet it spent its whole life resisting. There is no violence in it. The cold was never cruel. It only ever had to wait, and now the waiting is over. I want to linger in that quiet for a moment, because there is something in it worth feeling rather than hurrying past. For nearly 60 years, the spacecraft will have been in a constant, low, steady struggle. Its small fire pushing out warmth, the emptiness slowly drawing it away, the two held in a balance that the engineers fought to maintain degree by degree. And then, at the end, the struggle simply stops. Not because anything failed dramatically, but because the fire finally grows too gentle to keep ahead of the leak, and the balance tips for the last time, and the warmth begins its slow, unopposed departure into the dark. There is a kind of rest in that, the way there is a kind of rest when any long effort finally ends. The machine spent its whole life holding its warmth against the cold, and now it stops holding, and lets go, and the letting go is peaceful. The temperature inside drifts down, slowly, over years, past the point where the fuel would freeze, past the point where anything could work, down and down toward the temperature of the emptiness itself, until at last there is no difference between the inside of the spacecraft and the space around it. The fire that was lit before 1977, that burned without pause across half a century and 16 billion miles, quietly reaches its end, and the machine becomes, for the first time, simply another cold object adrift among the cold, and yet even that is not really an ending, which is the strange and wonderful thing. Because going cold is not the same as stopping, and still the spacecraft drifts on. This is the thing that astonishes me most, and the thought I most want to leave you with tonight. Voyager, cold and silent, will keep travelling for a length of time that makes the whole span of human history look like a single breath. It will drift for tens of thousands of years before it even passes near another star. In roughly 40,000 years, it will come within a couple of light years of a small, quiet star, closer to that star than to our own sun, though still so far from it that the star will not warm the spacecraft at all, will barely register as more than another point of light on its cold hull. Try to hold that stretch of time in your mind, because it is almost impossible, and the difficulty is exactly the point. 40,000 years. That is longer than all of recorded history many times over. When Voyager finally drifts past that distant star, everyone who ever knew the spacecraft existed will have been gone for an unimaginable span. The languages we speak now will be long forgotten. The countries that built it will be ancient memory or nothing at all. Whole civilizations could rise and fall in the time it takes the machine simply to coast past one neighbouring star, and even then it will barely have begun, because beyond that star lie millions more, and beyond them the slow turning of the entire galaxy. The spacecraft will keep going through all of it, cold and silent and patient, long after the last person who could have told its story has fallen quiet too. There is something almost dizzying in that, a span of time so far beyond a single human life that the mind simply slides off it and cannot find a grip. And yet the machine will live inside that span as calmly as it drifts through the next quiet hour, enduring, carrying its small message, indifferent to the emptiness the way only a thing at rest can be. It has already outlasted its maker's plans tenfold. Now it prepares to outlast their whole world, and ours, by a margin we can write down but never truly feel. And it will not stop there either. It will drift on, for millions of years, and then billions, looping slowly through the galaxy, long after the mission is forgotten, long after the people who built it are gone, long after, perhaps, there is anyone left to remember that it was ever made at all. And it will carry, the whole way, the thing it was given to carry. Bolted to its side is a golden record, a disc holding sounds and images and greetings from the world that made it, chosen and assembled with great love as a message to whatever might one day find it. That record was designed from the start to outlast everything else about the spacecraft. It needs no power, it needs no warmth, it does not depend on the fading fire at all. Long after the last watt is gone, long after the machine has cooled to the temperature of the dark, the record will still be there, its grooves still holding a birdsong, a heartbeat, a greeting in dozens of languages, a photograph of a child drifting on through a silence that will not decay it. The part of Voyager that could speak has a countdown. The part of Voyager that only listens and remembers and carries has no countdown at all. We built the fire to fade. We built the message to last forever. I find an unexpected comfort in that, and I hope you do too, lying there in the dark. The warmth was always going to fade because warmth always does. But we were clever enough and tender enough to also send something that does not depend on warmth, something that asks nothing of the fire, something that will keep drifting and keep carrying its small piece of us long after the last ember has gone cold. It is as though we knew, from the beginning, that the fire could not last, and so we quietly packed a second kind of message, one made not of heat and power but of gold and patience, one built to survive the very cold that would eventually take everything else. The voice will fall silent, the record will drift on, and somewhere out there, for a span of time we can barely name, a small cold machine will carry a warm message through a dark that finally, gently, holds it. So the fire fades, and the voice ends, and the spacecraft drifts on into a silence measured in billions of years, still carrying its message, at rest at last in the cold it spent its life resisting. That is where Voyager is going in the end. But before we let it drift away into that long quiet, I want to come back one last time to the small warm thing it is right now, tonight, still glowing, still speaking, still saying I am still here across the emptiness. Because the story of why it refuses to die is not really, in the end, a story about a machine. It is a story about us, and about the strange and lovely thing we did when we lit a small fire and sent it as far into the dark as we could reach. Let me tell you what I think it means. Part 12. What it means. We started with a simple question, one you may have clicked on almost as a joke. Why hasn't Voyager frozen? And the answer turned out to be two answers wearing the same face. It has not frozen because it carries a private fire that asks nothing of the universe, a warmth born from matter quietly falling apart, wrapped in the perfect insulation of empty space, which cannot steal that warmth by force and can only wait. And it is dying all the same, because that fire fades on a clock fixed before it launched, a countdown that cannot be paused or refilled or bargained with, spending itself in the very act of keeping the machine alive. The reason it lives and the reason it dies are the same reason. The fire is the hourglass. That is the whole of it, and it is strange and beautiful and a little sad all at once. But I told you this was really a story about us, and I want to close there, because I think the small machine has something to say to the ones who made it. Consider what we actually did as a species in 1977. We took a fire, a small self-sustaining warmth, and we placed it inside a machine, and we flung that machine as far into the dark as we possibly could, not to conquer anything, not to profit from anything, but simply to see, to reach, to send a warm and speaking thing out past the edge of everything the sun holds on to, and to keep it company with our listening for as long as its warmth would last. And it has lasted nearly 50 years. A small fire, alone in a cold with no edges, holding on far longer than anyone dared hope, still glowing, still speaking, still saying, tonight, across 16 billion miles of nothing, I am still here. There is a mirror in that, if you want to look into it, and I think it is why this story reaches people the way it does. Because you too are a small warm thing holding out in an indifferent dark. So am I. So is everyone you have ever loved. We run on fires we did not light, warmth borrowed from the slow processes of the universe, and we cannot refill the fuel, and the clock was running before we ever arrived. We hold on with everything we have, tended by the people who love us, and we are running down anyway, gently, on a countdown none of us set. And none of that is a tragedy. Or if it is the same tragedy that belongs to every star and every ember and every living thing that has ever been warm. The universe is mostly cold and mostly empty and mostly indifferent. And into that, here and there, for a little while, a warmth appears and holds on and reaches out. And the wonder was never that the warmth ends. The wonder is that it happens at all, and that it lasts as long as it does, and that it reaches as far as it can before the dark, patiently, gently, takes it back. I think this is why we built it in the first place, though we might not have said so at the time. We did not send Voyager out to a cold with no edges because it was useful, not really. There was science, yes, and there were planets to photograph, but underneath those reasons was something harder to name. We wanted to reach. We are a warm and curious and frightened kind of creature, aware, as no other creature seems to be, that the universe is enormous and old and mostly empty, and that our own warmth is small and brief. And rather than let that knowledge crush us, we did something almost defiant with it. We took a fire, and we sent it out past the last planet into the emptiness, as far as we could throw it, as if to say, even here, even in the coldest and loneliest place we can reach, there will be a little warmth, and it will be ours, and it will keep speaking for as long as it can. Voyager is that gesture made real. It is our warmth, and our voice, and our refusal to be silent, carried farther from home than anything we have ever made. It is the most human thing imaginable, disguised as a machine. So when its fire finally fades, I do not think the right response is only sadness. There is room for something closer to pride and to peace. We lit a small fire that could not last, and we made it last nearly 50 years. We sent a small voice into a silence that could have swallowed it, and we heard it call back across 16 billion miles for decade after decade. And we sent along with it a message built to outlive the fire entirely, so that even when the warmth is gone, something of us keeps drifting outward, patient and golden and unafraid, into a dark that will carry it for billions of years. That is not a failure. That is about the most that any warm thing can hope to do against a cold this large. Hold on as long as you can. Reach as far as you can. Leave something behind that lasts. Voyager has done all three, better than we had any right to expect. So the next time you hear that Voyager is still out there, still transmitting, still refusing to go quiet, I hope you feel what is actually underneath that headline. It is not just an old machine beating the odds. It is a small piece of us, a fire and a message and a promise, carried farther from home than anything we have ever made, kept warm and kept speaking by its own quiet stubbornness and by the devotion of people who will never touch it. It is proof of what a warm thing can do in a cold universe if it holds on and if it is loved. And when its voice finally fades, sometime in the years ahead, and the great dishes fall silent, and the small fire cools at last into the dark it spent its life resisting, the machine will not truly be gone. It will drift on, cold and quiet, and carrying its golden message for billions of years, through a silence deeper than we can imagine, long after the fire and long after us. The cold was always going to win in the end. It has all the time there is, and warmth is always finite, and the hourglass always empties. But not yet. Tonight, right now, as you drift towards sleep, there is a small warm machine at the farthest edge of everything we know, glowing faintly in the dark, still holding its fire, still turning its patient face toward home, still saying the only thing it has ever really said across all these years and all this distance. Still here, still here, still here, and for a little while longer, against a cold with no edges and a countdown that cannot be stopped. That quiet warmth goes on, reaching back toward us, refusing for now to let the dark have the last word.